We need to spend a little time calculating solubility or calculating Ksp's given solubility. And the good news is for these early problems, they're some of the most intuitive and least complex equilibrium calculation problems we do. And so I'm just going to jump right into a few examples here. And there's two basic scenarios, right? Given Ksp, calculate solubility, or given solubility, calculate Ksp. So that is what we have. I've got a new piece of paper here, and this is an old pen, so goodbye to that. We'll start out with a pretty simple example, like the problem for each of these. For the first ones here, let's just say given, calculate solubility, right? And that is S given Ksp. And solubility, as we mentioned in a previous video, solubility as like a property is the ability to dissolve into something, right? And we distinguish between dissolving and dissociating as being related terms. But in this case, when we're talking about solubility, we're talking about the specific thing that is how much can be dissolved. Another name for this would be molar solubility. And the molar solubility, and this will make more sense once we see some numbers, is really just the number of moles of solid that dissolve per liter of solution. That's what solubility means. So we're looking for this mysterious S value, solubility. All right, and let's use some real numbers to make this happen. First example we'll look at, let's take like manganese carbonate. I tried to pick compounds I don't normally do. So for example here, let's work with manganese carbonate, MnCO3 solid, and it has a Ksp value of 8.8 times 10 to the minus 11th. So this this K value I got from a table somewhere, nothing fancy. Every single problem is going to work like this. Solubility, write the aqueous dissociation expression. We have the MnCO3, it's a solid. It's going to give us Mn2 plus and CO3 2 minus. Our Ksp is just going to be the products over reactants to their coefficient powers. Our reactant's a solid, it's not going to appear in the equilibrium expression, so we only have these products. These products give you a product, and it's a solubility product. I'm laughing because they are the products, and we are multiplying them. That is a product, and the K for this case is called a Ksp, a solubility product. Anyway, this number is 8.8 times 10 to the minus 11th. These are going to be ice problems, all right? Initial change, equilibrium, Q's and K's, whatever you want to call them. We're not worried about the solid because it's a pure substance. We're starting out with none of those things. This will dissolve, in this case dissociate, to produce those things in a 1-to-1 ratio. And instead of using X, we're going to use S. You could use X, but X solubility doesn't start with an X, it starts with an S. That's why things are done, I guess. S plus S, so we end up with S, and we end up with S. In this case, then, that is S times S equals 8.8 times 10 to the minus 11th. And then just take the square root of 8.8 times 10 to the minus 11th, and you get S equals 9.4-ish times 10 to the minus 6th. K values are unitless. Solubilities do have a concentration, and that is a molarity. We'll call this example A. And that molarity, what we are really saying is that there are 9.4 times 10 to the minus 6th moles of this manganese carbonate that will dissolve per liter of solution, and it will give you these ions here. And I'm not going to look at the S corresponding to those right now. This S corresponds to this, which turns into those. All right, and that may be a bit semantic in distinction, but it's important. We'll talk about that in a bit. Second example, I just want to change up our coefficients a bit. So we'll do something like silver phosphate. We'll call this example B. And if we were to look at our solubility rules, it says insoluble compounds, phosphates, yeah? Unless you have a group 1 or ammonium, which we don't. In this one here, we had manganese carbonate. Well, that's a carbonate that's not group 1 or ammonium, so these would be expected to be insoluble. But in reality, in this case, I end up with 9.4 times 10 to the minus 6th molar manganese ions and 9.4 times 10 to the minus 6th molar carbonate ions. It's not insoluble, it's just not producing many ions. It's not good at being soluble. Ksp, in this particular case, is 1.8 times 10 to the minus 18th. Exact same format. We're going to write an aqueous dissociation equation, and again, that's a strategy that I recommend for every single equilibrium problem. Write your equilibrium expression, write a Ka equation, set up ice, and then plug in what you have. It gives you a place to put things. It's very logical, and you always have a plan. All right, I wrote manganese. So we have Ag3PO4. That's a solid. It's going to dissociate to give us 3 silver ions and a phosphate ion. And so our Ksp expression is going to be those silver ions. And this time, since it has a coefficient that's cubed, right, products over reactants to their coefficient powers, that's Ag plus cubed and PO4 3 minus. And our value I gave as 1.8 times 10 to the minus 18th. And that is unitless. K values are unitless. We talked about that in a separate video. Let's take care of our ice problem as promised. In this particular case, we're not worried about the solid. It doesn't have a concentration per se. Our silver ions are starting out at 0 because we haven't made any yet. Our phosphate ions are starting out at 0 because we haven't made any yet. Once this dissociates, once this dissolves, this is going to go up. The equilibrium is going to shift right. This is a Q value of 0. This would be a Q value of 0. So the equilibrium has to shift towards zeros to make them go away to increase that Q value. All right, so this is going to go up by not S, but 3S because of that 3 right there. And this is only going to go up by S. We end up then with 3S and S. In this case right here then, we have 3S quantity cubed times S equals 1.8 times 10 to the minus 18th. And you can just plug that into the calculator or whatever. You can simplify it a little bit and say that's 27s to the 4th equals 1.8 times 10 to the minus 18th. But you end up with your S value of 1.6 times 10 to the minus 5th molar. And that is our solubility of silver phosphate. As a little side note, you can just note like, that's 10 to the minus 11th, and that's 10 to the minus 18th, but that is actually more soluble. And the reason being it's total ions that you're producing, right? This is only producing 2 ions per mole of this that dissolves, and this is producing 4 ions per mole of it that dissolves. So we end up with the smaller number there, but a bigger number there comparatively. All right. And by the way, once again, this is not the concentration of silver ions. That's not what we're saying. We're saying that 1.6 times 10 to the minus 5th moles of this will dissolve or dissociate into 1 liter of water, which will give us these concentrations right here. So be very careful with that idea. And I'll mention it one more time in a bit here. Let's see if this can work. We'll fit it on the page. We'll do one that's got semi-uglier coefficients. When we split it up, we'll call this example C. Strontium phosphate, Sr3PO4 2, and that's a solid. It has a Ksp value of 1 times 10 to the minus 31st. Not very soluble, but again, it might give us a solubility value that is higher than we're expecting because we got a whole bunch of ions. We got 5 ions it's producing. There we had 4. There we had 2, for instance. None of those words really matter unless we're looking into the future. We've got strontium phosphate, Sr3PO4 2. It's going to dissociate to give us strontium ions, 3 of them, and phosphate ions, 2 of those, with a Ksp value of 1 times 10 to the minus 31st. All right? Set up our equilibrium equation, strontium ions cubed and phosphate ions squared. So we set it up just like all those other ones. We're going to do an ice problem. We're not worried about our solid. We don't have any of those things starting out. This is going to go up, right? As we shift right, those zeros will increase. So that's going to go up by 3s, and that's going to go up by 2s, right? And then we're going to end up with 3s there and 2s there. And then this is 3s quantity cubed and 2s quantity squared equal to 1 times 10 to the minus 31st. All right? And again, you can punch that into solver or whatever. You can save yourself a little bit of effort if you expand that as 108 s to the 5th is 1 times 10 to the minus 31st. And we find out in this case that the solubility is 2.5 times 10 to the minus 7th. Solubility is 2.5 10 to the minus 7th molar. Solubilities do have a unit, as I said. So there we go. That's the solubility for those three things. This for strontium phosphate, this for silver phosphate, and this for manganese carbonate. Those are our solubility values. And what I want to do now is take a look on the other side. What happens if we're given a solubility and we want to come up with that Ksp value? And the good news is it's pretty much the same problem. Just going to wave our hands a little differently once we get to that point. It doesn't really matter what colors I choose here, but I'll try and vary it up a little bit. Over here, we're going to say calculate Ksp, or they might say find Ksp, given the solubility. And that is S, our molar solubility. Our first example then, let's give this a try, is going to be something like maybe gold chloride. AuCl has solubility 4.47 times 10 to the minus 7th molar. Find Ksp. All right, so that's the generic setup for this problem, or for all these problems that we're about to do. Start out, say, oh, I don't know what to do. Okay, we'll write your aqueous equilibrium expression, and then go from there. In this particular case, AuCl, Au plus, and Cl minus. Write your Ksp expression. In this case, that's the Au plus times the Cl minus, and that is what we're looking for. We're going to do everything that I said previously, which is write your dissociation equation, write your K equation, set up your ice problem, and then you have a place to put things. If you look right here, I don't have any of that, I don't have any of that. It will go up by some amount, it will go up by some amount, and we will end up with that amount and that amount. And over here, that will be S, and that will be S, and that's going to equal Ksp, the value that I actually want to know. We'd be stuck here if we didn't already know what that S was, right? This is S. And so all we have to do is plug this in, 4.47 times 10 to the minus 7th molar, and it's over 1 molar to make the molarities disappear. I'm not going to write that. 4.47 times 10 to the minus 7th molar, and that's going to be our Ksp. In this particular case, that is 2 times 10 to the minus 13th. So Ksp is 2 times 10 to the minus 13th. And that is unitless, as all K values are. We'll say that that is our answer to example C, right there. Oops, sorry, D. We already did C. Again, following the same line of reasoning, we'll just up the difficulty again just a bit and say we've got some different ratio of ions. Like maybe we'll go magnesium fluoride. We'll say MgF2 has solubility 1.17 times 10 to the minus 3 molar, right? Find Ksp. And it's the same setup every single time. Any equilibrium problem at all is going to be write your equilibrium expression, write a K equation, set up ice, and then plug stuff in. In this case, that's MgF2. Magnesium ions. And 2 fluoride ions. Our Ksp is supposed to be the magnesium ions. And this is where it's slightly different than the previous example. We have our anion, but we have 2 of them. And I'm still looking for that Ksp value. From there, everything's exactly the same. Set up the ice problem. Not worried about those. Didn't have any to start with. Went up by S, but this time it went up by 2S. And so we end up with S and 2S. And that's what these values are right here. I'm going to have S times 2S squared, and that's going to be Ksp. And our S is right there, so I don't really want to write that, but our Ksp value ends up being 6.4 times 10 to the minus 9th. Call that example E. And then one more example. And we'll be all set for generic find solubility and generic find K using the solubility. We'll set up maybe lead phosphate, Pb3PO4, 2, lead 2 phosphate, as solubility 3.74 times 10 to the minus 10th molar. Find the Ksp. Write your equilibrium equation, your aqueous dissociation in this case. We've got Pb3PO4 2 solid, giving us 3 of those lead ions and 2 of the phosphate ions. Our Ksp is going to have to be the lead ions, but cubed, and the phosphate ions squared. And I don't know what that Ksp value is. We know how to get it though, just like we got all the other ones. Set up your ice expression. Not worried about that. Starting out with none of those things, we're going to add 3s because of that 3. We're going to add 2s because of that 2. We end up with 3s and 2s, and when we plug those in, that's going to be 3s cubed and 2s squared equals our Ksp. This is s right there, and so I'll plug it in right there and right there, and we end up with our Ksp equal to 3 times 10 to the minus 44th, which is pretty impressive, 10 to the minus 44th. We'll call that example F. That'll be example F. And that pretty much exhaustively deals with simple solubility calculations, simple calculating K expressions. In the next video, we'll take a look at common ion effect, and then after that, we'll look at some complex ion stuff, and then look at the whole big picture. But this is done here.